Okay, so we are going to talk about chapter 8 today, which is our chapter on gases. Um, we're going to talk through some of the properties of gases, and then we're going to talk through how we do some calculations with them. Um, we're going to use what's called the kinetic molecular theory to help us figure out why gases behave the way that they do. We're also going to look at some different types of measurement units that we're going to use when we're talking about pressure, which is one of the most common properties that we associate with gases. When you're thinking about gases, there's a few properties that you want to be familiar with. You want them to stand out to you, okay? When you're talking about gaseous matter, which is a fancy way to say gases, you're looking at atoms or molecules that have a ton of empty space between them. All right, most of your gas samples are, it's actually just empty space. All right, and these gas particles, whether they're atoms or molecules, are able to move freely relative to one another, and they're really constantly in motion. Gases are going to be compressible. That's another one of their properties. When something's compressible, it means that you can take that substance and you can kind of squish it down so it fits into a smaller space. Okay. The reason why gases are compressible is because of all of that empty space between the particles. So when you squish them down, they're just going to get a little bit closer together, but there's still room. Another property of gases is that they are always going to take the same shape that their container has, and they're going to fill the volume of their container. All right. Where your solids and your liquids are going to be constrained in either one or both of those ways, gases can move around. So if they're contained inside of a spherical sort of container, that'll be their shape. If they're in a cubic container, that'll be their shape. Unlike liquids where there's going to be a limit, like there's a specific volume associated with your liquid substances. When your gases are put into a container, they will spread out as much as possible. That's why we're saying that their volume will mimic whatever the volume of their container is. This is kind of an example of what you can visualize when you're thinking about gas molecules in general. Whether your gases are molecules or atoms, it's kind of easier to just picture them as particles. And they're like particles that are constantly in motion, and they're particles that are going to move in straight lines until they collide with something. All right. The things that they can collide with are the surface, one of the surfaces of the container that they're in, or they can collide with each other. All right. When you have a gas particle colliding with a surface, the result of that collision is going to be pressure. Okay, because pressure, if you look at the formula for pressure, you don't have to worry about calculating with this formula right now. I just want you to understand where the pressure comes from. Pressure comes from a particular force being applied over a certain area. Okay, so when these particles are hitting the surface, they're hitting with a certain amount of force behind them, right? So that force over area relationship is how our pressure is going to be formed. And the more collisions with the surface that our gas particles have, the higher our pressure values are going to be. So when you think about gas and you think about pressure, what you really want to focus on is anything that increases the number of collisions of my gas particles is a thing that will increase my gas pressure. All right, those things are linked. We have some particular properties, or not properties, but factors that can specifically affect the pressure of a gas. And that's because each of these factors is something that will change the amount of collisions that our gas particles are having. Okay. We'll go through these just one at a time. The first factor would be the number of gas particles that's in a particular container. So you have to think about this like you could think about gas particles kind of like they're people, right? If you have a whole bunch of people crowded together in a small space, when they're moving around, they're going to bump into each other more. Same thing with your gas particles. If you increase the number of gas particles that's in a certain container, you're going to have more collisions with the different walls of the container. All right. As you decrease the concentration, you reduce the number of gas particles that are present. Then there will be fewer collisions and our pressure will decrease. All right. Another factor is the volume of our container. If we increase the volume of our container, we're going to give our gas particles more space to move without finding something to collide with. All right. So anything that reduces the number of our collisions reduces our pressure. So if we decrease our volume and we make everything a lot smaller, then we're removing a lot of our free space. So now when our gas particles move around, they're finding the walls of the container and they're finding other gas particles a lot easier. So they're going to collide with more things. All right. So reducing that volume, making our container smaller is one way to increase the number of collisions that our particles are having, which means that we're going to have higher pressure values. All right. The third factor that's going to really impact our pressure is going to be the speed that the gas particles are traveling. And that's because the faster the particles go, the more force they're going to have when they collide. And, force and pressure are related. But additionally, the faster that particles are moving, the more collisions they're just going to have numerically because they're going faster. So they're going to get to the walls of the container faster. And so the faster the particles move, again, the more collisions they're going to have and the higher those pressures will be. Okay, so those are the main factors that are going to affect our gas pressure. Now there are certain, we'll call them like tenets or points of the kinetic molecular theory. They're parts of this kinetic molecular theory that explain behaviors. All right, so we have our gases. Gases consist of small particles, like we mentioned before. And the first point of this kinetic molecular theory is that our gases are going to move randomly at all times with very high velocities. This random movement, to kind of connect it to point number 4 here, is going to be in straight lines, and the movement is going to be constant. All right, gases never like take a break; they never pause. Our second point of our kinetic molecular theory is that our gases are going to have very small, pretty much non-existent attractive forces between them. Okay, so the way that most molecules sort of work, think about it this way. You have two particles, okay? And let's say that they're like a solid or a liquid or something. When those atoms are close together, they're going to have like an attractive force, some kind of attraction between like the protons in one of them and the electrons in the other. We've talked a little bit about it, the intermolecular forces that can be at work. Is there hydrogen bonding? Is there a temporary dipole that's forming? Just something. And in solids and liquids, the particles are so close together that these attractive forces, they become an important part of the property of the substance, because the molecules or the atoms spend so much time near each other. But with gas particles, they're moving around like this, like all the time, like so fast. And there's no time for any of those attractive forces to develop. And so that's where that second point comes from. The reason why those attractive forces are so small, whether they're attractive or repulsive, but the forces between your gas particles are so small because the gases, they are moving very quickly and there's a lot of empty space. So they're not really spending very much time near each other at all. Gases are also going to occupy a much larger volume than the volume of the molecules or the atoms by themselves. So if you had a sample, I don't know, let's say that we have a container that's like this big, okay? You have, let me just pause that real quick. You have all of you have like these gas particles that are moving around your container, right? Pretty small. What that last point says is that like we would consider this entire volume the volume of our gas. Whatever the volume of our container is, that is the volume of our gas because our gas particles can expand to fill whatever container that we have them in. But when you compare the amount of empty space to the actual volume of the particles that make up the gas itself, the open space, the free space is going to be significantly larger than the volume of the gas particles. Like if we put all of these four things together, that's how much space our gas is taking up, and all of this other space is just empty free space. But that's how gases work. They spread out, they take up a lot of room, and they stay kind of far away from each other because they have all of that empty space. All right, we already talked about the constant motion and straight lines. The last point is our gases are going to have a Kelvin temperature. All of our gas calculations that involve temperature, you have to remember that all of our temperatures have to be in terms of Kelvin. But what we're going to see with this temperature is that our gases are going to have a temperature that's proportionate to the average kinetic energy of the molecules. Average kinetic energy is going to talk about the relationship between the mass and the speed of our gases, okay? Mass times velocity. I'll look up the equation. I don't want to say it wrong for you here, but there's the mass of our gas particles and their speed are related to their overall kinetic energy, which is their energy of motion. And what you see with gases is that as you increase the temperature of the gas's environment, the average kinetic energy of those gases always increases as well. All right, so temperature goes up, average kinetic energy goes up. All right, which means that kind of makes sense because it means that your gases, you're heating them up, your gases are moving more and they're moving faster. Kinetic energy is the energy of motion. All right, so all those things are linked together. This is just a little summary of the properties that we're using to describe gases. And you'll see that some of these properties have units of measurement that are specifically associated with them. And this is a good summary to remind you of like what units we should use when we are doing our gas calculations, okay? We probably could be a little more specific up in here too, and I'll show you the specifics in a few slides, but when you're calculating pressure or when you're describing pressure, there's a few different units of pressure that you could potentially use, and they're pressure units that you should be familiar with. They're very common pressure units. When we're looking at the volume of gases, we'll see those described in liters or milliliters. For temperature, we'll see gases described in Celsius, but we're going to use Kelvin when we do any gas calculations. And when we're talking about the amount of gas, we can talk about gases in terms of grams or kilograms or moles. notice this unit mole has a lowercase n here. That's its symbol. But when we're doing our gas calculations, we have to make sure that we're representing our gases in terms of moles only, okay? So we can't plug gram values into our gas calculations. All right, but we'll go over more of that in a second. You guys haven't even seen the equations for those yet. So let's just look at some of the properties. Volume of the gas. When we talk about the volume of the gas, we're talking about the same volume of whatever the container is that the gas occupies, measured in liters and milliliters. And what we're going to see is that the volume is of a container that's holding a gas is going to increase if our temperature increases, as long as our pressure stays constant, right? Imagine that you're trying to keep the gas pressure constant, meaning you're trying to keep the number of collisions constant. If you increase the temperature and the gases start to move faster, how can you stop the number of collisions from increasing along with that increased movement? The only thing you can really do is expand the volume of your container as well, right? Assuming that it's a container that you can change the volume of. A picture like a balloon, right? Balloons can expand and contract. If you take a balloon that's inside of a really cold air-conditioned store and then you walk outside with it into a really hot summer day, you'll see that balloon expand, right? And that's because our atmospheric pressure doesn't change. So our pressure is constant. That means that all of those gas particles, like they're moving faster, but our pressure is the same. So what's going to change? The volume of our gas is going to change. And then, sometimes when you have a really hot day and there's not enough space in the balloon for it to expand anymore, it pops so that the gas particles can leave, right? Because you can't break the rules of pressure. For our temperature, we're going to see that, again, this is going to be related to our kinetic energy, and it's going to be measured in Kelvin. And the connection that you're going to make here is that when our temperature of a gas decreases, our molecules are going to collide less, which will kind of lead to a decrease in pressure. And when our temperatures increase, our molecules will collide more, and that would lead to an increase in pressure. Pressure itself is going to be a measure of these gas particle collisions with the walls of our containers. And these are all the different units that you can measure pressure in, okay? Some of them you'll be more familiar with than others. The unit of atmosphere is the kind of universal unit. But if you're familiar with like your car tires and stuff, you'll always see pressure measured in PSIs, pounds per square inch. So that's a good pressure unit to be familiar with. And we also have the pressure that we experience sort of every day all around us. The gas particles in the air are exerting pressure on us. Okay, so that type of pressure that we're experiencing constantly is called atmospheric pressure. You can measure atmospheric pressure by using an instrument called a barometer. And the barometer is going to basically it's like an open pool of, typically like when liquid mercury was used because it was just an easy substance to work with. And the liquid mercury would stay in this sort of open pool here. And the atmosphere is able to exert pressure on the liquid. And then as that pressure was exerted, we have a little, a tube here with a vacuum in it. The vacuum meaning that all of the air was removed from this tube, this container, looks like an inverted test tube, but all the air was pulled out of it before this process, so that's completely empty space. And the gases in the air will push down on the surface of the liquid mercury. And as that happens, the liquid mercury will start to move into this cylinder and will move up it, and it will continue to kind of creep up the cylinder like this until no more pressure is being exerted by the atmosphere. And the way that we measured atmospheric pressure initially was measuring the height that the mercury was able to reach in this barometer. Okay. So when you see a pressure reading like this, where it says like 760 millimeters of mercury, the mm is the millimeters and the Hg is the mercury, they're literally saying that the distance from the pool of liquid mercury up until the meniscus of the mercury, the highest level it was able to reach, that distance was 760 millimeters. Okay, so that became the standard for atmospheric pressure. All right, that unit, 760 millimeters of mercury, that is going to be equal to 1 ATM, the unit atmosphere. All right, so 1 atmosphere is equal to 760 millimeters mercury. Now, on a side note, the inventor of the barometer, the last name Torricelli, this portion of their last name got pulled off and is also used as a unit, basically, which can get confusing. So when you say that the pressure is 760 millimeters of mercury, you're literally referring to the height that the mercury rose. If you say 760 torr, you're saying the same thing. You're just calling the millimeters of mercury by the name of the person who first used the barometer to measure pressure. Okay. These two units are used interchangeably. So you can switch back and forth between millimeters of mercury and torr without doing any math at all. All right. Here are some other pressure units that are common. You do have to be able to use all of these units in calculations. So they're written out this way. They're telling you the unit name, the abbreviation that's common. Note down here, you can shorten the pounds per square inch to the symbols, or you can use the abbreviation PSI. And then the numbers that are here tell you exactly how many of each of these types of units of pressure are equal to 1 atmosphere. All right. The reason why we equate everything to 1 atmosphere is because atmosphere is the pressure unit that we're going to need to use once we start working with our gas laws, specifically our ideal gas law. This is just another way that we can look at that chart. I wrote them as unit equalities instead. So what you're seeing here, 1 atmosphere, 760 millimeters of mercury. 1 atmosphere is 760 torr. All right, so you can read that last chart that we have here. All of this is the same information. Okay, they're just listed in terms of the unit equalities instead. This is another visual of some atmospheric pressure. Probably not a surprise to you that at different elevations, the atmospheric pressure changes. Okay. We're going to see that the closer you get to the surface of the Earth, the more pressure is going to be exerted. So if you take pressure readings that are at sea level, those pressure readings are going to be a lot higher than if you go up to the top of a mountain, right? We're further away from the surface of the Earth. So the pressure that the air is going to be exerting at that elevation is going to be less. So our pressures, our atmospheric pressures are going to decrease as our altitude increases for that reason. And if you're at sea level, then your atmospheric pressure is usually right around 1 atmosphere. These are just some of the other locations with different altitudes listed and their corresponding pressures. So you see somewhere like the Dead Sea that actually has an altitude that's below sea level, has an even higher atmospheric pressure. But once you get up to like the top of mountains, or even if you've ever gone to like Colorado, if you've gone to somewhere like Denver, and you just try to like walk around in the street there, you'll notice the difference in the atmospheric pressure, because a lot of times you'll run out of breath a lot faster in a place that's at a higher altitude. And that's because you're used to breathing with an atmospheric pressure right around 760. Okay. Other things that we can look at. On hot days, our mercury column is going to rise, indicating a higher atmospheric pressure. That's because when temperature increases, pressure increases. On rainy days, the atmosphere is going to exert less pressure and our mercury column is going to fall a little bit lower. So just some interesting things to note there. Let's take a look at these first 2 questions in the learning check. We're just looking at some pressure conversions here. All right, so we'll write out the conversions that we want to make, and then we're going to look back at our table and we're going to find the equalities that connect the pressure units that we're looking at. Okay, so question 1, let me pause the screen sharing a second. Question 1 has us going from 475 millimeters of mercury into atmosphere. And question 2 gives us a pressure of 2 atmosphere and wants us to convert that into millimeters of mercury. Okay, and so when you look back at your table of pressure equalities, you'll see that 760 millimeters of mercury equals 1 atmosphere. So we can use the same equality for both of these questions. All right. And the way that you set this up is the way we set up any of our qualities that we've worked with so far. Start with or any of the conversions we've done. You start with the information that you're given, including the unit. And then when you set up your conversion factor, whatever unit you're working with here is going to go on the denominator section of your conversion factor. So our 760 millimeters of mercury goes on the bottom. And our 1 atmosphere goes up top. And then we calculate that out. And we have a pressure of 0.625 atmosphere. Okay. In our second question, our starting value is in terms of atmosphere instead of millimeters of mercury. Okay, so we start by writing out the number that we're given. And when we set up our conversion factor, the value with this unit goes in our denominator. So now 1 atmosphere goes in our denominator. And 760 millimeters of mercury goes up top. Right? And you see that in both of these calculations, our initial pressure unit cancels out, and we're going to be left with the one that we want. Okay. All right. So let's look at something a little different. We're going to start looking at some of the gas laws. Share that again. And our introduction to the gas laws here is going to be through what are usually called the simple gas laws first. And our simple gas laws are going to be a set of relationships that connect two gas properties to each other. And that connection is going to be true as long as the other gas properties are held constant. Okay? So for example, with Boyle's law, our first one here, this is going to show us the inverse relationship between pressure and volume. Okay, so what does inverse mean? It means that they have an opposing relationship. When one of them increases, the other property is going to decrease. Okay, that's what our term inverse is going to mean. And when we're looking at Boyle's law, we're specifically looking at the pressure and volume relationship. We're focusing on pressure and volume. But our temperature and gas amount, those things do not change when we're using Boyle's law. Okay? And because Boyle's law is showing us this inverse relationship, what that means is a little arrow here. When pressure increases, then volume is going to decrease. Okay? When pressure decreases, then volume increases. Okay? Assuming that our other two factors are staying constant and not changing. All right. The equation for Boyle's law, I'll write it out here for us since we're going to do a practice problem in a second, is written like this. P1 times V1 equals P2 times V2. All right, so we're only looking at pressure and volume changes. And if we have an initial pressure and an initial volume, and this pressure goes up, then this volume has to go down. Because the product of this multiplication has to equal the product of this multiplication. So let's look. Let me show you the slide again, just so we could look at the picture here. What you're looking at here is a good representation of Boyle's law, because they're saying here, like, we have a cylinder that has a piston on it, so the roof of the cylinder can like basically go up or down, changing the volume that's in the container. So when it's elevated all the way, our volume is going to be 4 liters, and the pressure of our gas particles is only going to be 1 atmosphere, because they have a lot more room to move before they're going to collide with the surface. In our second scenario, we've moved that piston down and we've decreased the volume, cutting it in half. And by cutting it in half, now the gas particles have a lot less space to move around, so they're colliding with everything a lot more. And now our pressure has doubled. Okay, so we decreased the volume and we've increased the pressure. And that's really what Boyle's law is showing us. So you can see here, you have these, like in this case that they're giving us here, they're showing us like one sample of gas, but they're changing the volume in each scenario. So say that you have a setup similar to what we were just looking at before. If we have 2 liters of that gas that's at a standard temperature and pressure, then our pressure is going to be 8 atmospheres. Okay, but if we have that same sample of gas and now we increase the volume of the container, so now the gas particles have like 4 liters to move around in, our pressure decreases to 4 atmosphere. If we take that same sample of gas and we give it even more space to move around in, now it's going to collide with the walls of the container even less. So now the pressure is only 2 atmosphere. But in every case, if we take the pressure and we multiply it by the volume, we always end up with the same number. Okay. And the other important thing to always remind yourself of when we use one of these simple gas laws is that we're only changing 2 of those gas properties at a time. So like for Boyle's law, we're only focusing on pressure and volume, and our temperature and our amount of gas have to stay the same. Okay. There's a lot of processes that are linked to Boyle's law, even though we don't like normally talk about these processes in terms of our simple gas laws. But something like breathing, inhalation and exhalation, when you inhale, your lungs are expanding, so your volume is increasing. The pressure in your lungs decreases as a result of that. I just yawned, just talking about breathing made me yawn. Air flows towards the lower pressure in the lungs. Okay, that's your inhale. In your exhalation, you're going to be breathing out and your lung volume is going to decrease. And as your lung volume decreases, the pressure in your lungs will increase. And so the air is going to flow from the higher pressure in the lungs to the outside. Okay, so it's all connected. Let's take a look at this one. We have an example here of a calculation using Boyle's law. Freon 12, this is the formula, was used in refrigeration systems. What is the new volume after an 8-liter sample of Freon gas, initially at 550 millimeters of mercury? What's the new volume? Initially, after its pressure is changed to 2200 millimeters of mercury at constant temperature and moles of gas. So we started out with a sample that's 8 liters and 550 millimeters of mercury, and we're increasing its pressure to 2200 millimeters of mercury. If we're increasing its pressure, we're expecting a decrease in the volume. Okay. Excuse me. The 3 steps you can look at to solve this problem: you can state what was given to us in the problem and what we need to find. And then we can rearrange Boyle's law so that we're solving for that unknown volume. And then we can plug all of our numbers into that equation that we've just solved for, and we can calculate the new volume. So let's take a second and do that. So we have our original situation will be our P1 and our V1. So our original pressure was 550 millimeters of mercury. I like writing torr because it's shorter, but I don't want to confuse anyone. And our initial volume is 8 liters. And then our new pressure, pressure 2, is going to be 2200 millimeters of mercury. and our new volume is the question mark. Okay. So step one is listing out our information. Step two, they suggest rearranging this law so that we're solving for our unknown variable. So how do we isolate V2? We're going to divide both sides by P2. All right. So we divide both sides by P2. And now what we're left with is going to be P1 times V1 divided by P2 equals V2. All right. Not too bad. Now we're just going to plug our numbers in. So what we have here, 550 millimeters of mercury times 8 liters divided by 2,200 millimeters of mercury equals V2. And you see our pressure units are going to cancel out here. And the solution to this is going to be a volume of 2 liters. That is our new volume. All right, let's take another look at this learning check. Another example, we have a sample of oxygen gas that has a volume of 12 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36 liters at a constant temperature and amount of gas? All right, so let's run through our first step, which is going to be us organizing our information. Just erase that last bit from the last problem. So our original pressure is going to be 600 millimeters of mercury. Our original volume is going to be 12 liters. Our new volume is going to be 36 liters. And we're going to be looking for that new pressure. All right, so now we can rearrange our equation to solve for our new pressure, just like we did before. But this time, our pressures are unknown, so we'll divide both sides by V2. And now our equation is going to be P1 times V1 over V2 equals P2. Okay, and now we can plug in all of our pieces. So we have 600 millimeters of mercury times 12 liters divided by 36 liters. Our volume units are going to cancel out there. And we end up with a pressure of 200 millimeters of mercury. That's going to be our P2 value. Okay. Boyle's law is not too bad. Let's look at this next question. All right, this one says, for a cylinder containing helium gas, indicate if cylinder A or cylinder B represents the new volume for the following changes. Okay, so this is like a conceptual one. This is our initial container, so you see where our volume line is at. And in scenario A, our volume has gotten smaller. And in cylinder B, our container has gotten larger. Okay, so A represents a decrease in volume, B represents an increase in volume. And now this is just making sure that we're understanding that inverse relationship between pressure and volume. So if our pressure decreases, then we're expecting an increase in our volume. So that would be cylinder B. If our pressure increases, we're going to expect a decrease in our volume. So that's cylinder A. All right, we have another one. We have a sample of helium gas is a volume of 120 milliliters and a pressure of 850 millimeters of mercury. What's the new volume if the pressure is changed to 425 millimeters of mercury? Okay. So we'll try one more of these. Gonna write down the information first. This is just like how I like to sketch this out, visualize it. All right, now we can solve our equation for V2. So V2 is going to be equal to pressure 1 times volume 1 divided by pressure 2. So 850 millimeters of mercury times 120 milliliters divided by 425 millimeters of mercury. All right, and our pressure units are going to cancel out. And our new volume is going to be 240 milliliters. Whatever the units are here, that matches with the units that we're going to report here. All right, a sample of helium gas in a balloon. Oh, let me share that screen again so you can see what I'm seeing. A sample of helium gas in a balloon has a volume of 6.4 liters at a pressure of 0.7 atmosphere. At 1.4 atmosphere is the new volume represented by A, B, or C. All right, so now in this visual, this is our initial volume. So this volume is supposed to represent 6.4 liters. Balloon A represents a volume that's smaller. Balloon B represents a volume that looks to be the same. And balloon C represents a volume that looks to be larger. Okay, so now we're going to look at our pressure. Initially, our pressure was 0.7 atmosphere. And it looks like we have increased our pressure to 1.40. So if we've increased our pressure, we need to be decreasing our volume by a similar amount. So it would make sense that if this was our initial volume, that our new volume is going to be one that's smaller. So that is balloon A. All right, our next gas law is called Charles' law. It's the next one of our simple gas laws, and this is going to show the direct relationship between temperature and volume. Charles' law. All right, so remember that when we say direct relationship, we mean that the properties that we're talking about are going to increase together and they're going to decrease together. Okay. Direct relationship between temperature and volume. So in this scenario, when we're looking at Charles' law, the other two properties of gases, the amount of gas and the pressure of a gas, these things would be held constant, and we're only going to focus on the temperature and the volume. Okay. The formula for Charles' law looks like this. The reason the formulas are what they are will make more sense to you once we look at the ideal gas law. But when we are looking at Charles' law, we're going to be looking at the volume of the gas in scenario 1 divided by the temperature of the gas in scenario 1 will be equal to the volume of the gas in scenario 2 divided by the temperature of the gas in scenario 2. Okay? V1 over T1 equals V2 over T2. And the big thing here, once we get into Charles' law, is that this temperature has to be put into Kelvin before you can do this calculation. Okay? Your temperature must always be in Kelvin. So these are just ways that you can write out Charles' law. What they're showing you here is how you can solve for the different variables. If you wanted to rearrange Charles' law so that you were solving for V2, if you're trying to get V2 by itself, then you'd say, all right, well, I'm going to multiply both sides by T2 so I can move it over here. So what does that give you? Volume 2 is going to be equal to volume 1 times temperature 2 divided by T1. Okay, this part is just a little bit of algebra, but you want to be comfortable solving for whichever of these variables is the missing one. Okay. Let's take a second to solve Charles' law for T2. All right, in the example that they showed us, they solved for V2, but we'll solve for T2. All right, and that means that we have to have T2 on its own side with everything else on the other side. And T2 also has to be in the numerator spot when we're done. You can't have an unknown stay in the denominator spot. All right. So this is going to be the variable that we're going to be trying to isolate and to solve for. That means that even though you're going to want to move V2 first, you're going to look at this and you're going to want to focus on V2 and get it to the other side, you're going to ignore V2 right now. And we're going to focus on getting this temperature, this T2, into a numerator position. So we're going to multiply both sides by T2. And when we do that, you can think about it like when we multiply by T2, that's like saying it's going to be T2 over 1. And when we do this, you see how like it's going to cancel out on this side. But now on this side, what we're left with is going to be T2 times V1 divided by T1. And that's going to be equal to V2. But now that we have it set up like this, we've got our T2 value in the numerator spot. So now we can work on getting this stuff over to the other side. Okay. And how we're going to move it is we're going to multiply both sides by the reciprocal of the values that we want to shift over. So if we take this side and we multiply our terms on the left by T1 over V1, that means that these things will cancel out on this side. But whatever we do to one side of an equation, we have to do to the other side. So we have to multiply our right side by T1 over V1 as well. okay? And what we're left with when we're done with that is T2 is going to be equal to volume 2 times T1 over volume 1. All right? But you have to get that unknown value out of the denominator spot before you start to get it on a side all by itself. You can't skip right to the part where you get it all by itself and leave it in the denominator. Okay? All right, so let's look at a question, calculation question. Share that again real quick so that we can all see the question. All right, we have a balloon that has a volume of 785 milliliters at 21 degrees Celsius, and the temperature is going to drop to 0 degrees Celsius. What is the new volume of our balloon at constant pressure and moles of gas? Okay, so we start out with writing out Charles' law. Okay, and now in this case, we can label our variables. I think it's worth taking the time to just put everything into position. In this case, you're also going to want to pay attention to the fact that these temperature values that they've given us are in terms of Celsius. We need to do math with them once they've been converted into Kelvin. So to go from Celsius to Kelvin, we're going to be adding 273 degrees. But we have to do this step before we can do any calculations. And you can, again, like we just were showing before, we can solve for our unknown variable before we plug in any numbers. How do we get volume 2 on its own, isolated? We multiply both sides by T2. Okay? So think about this. If I'm trying to find volume 2, that means that I need to get it all by itself. So I'm going to multiply my right side by T2 over 1. So I can get rid of it from over there. And I'm going to put it on the left side. So now what I have left on the left side is going to be T2 times V1 divided by T1 equals V2. Okay, and now I can plug my numbers in. Temperature 2 is going to be 273 Kelvin. That's why I like having everything labeled like this, so I don't accidentally switch my T1 and T2, for example. So my T2 is going to be my 273 Kelvin. All right. My V1 value is going to be 785 milliliters. And then I'm going to divide it by T1, which is 294 Kelvin. Kelvin units will cancel. And my V2 is going to be equal to 729 milliliters. Okay. not too bad. Let's try one where we are going to find an unknown temperature instead. Okay, so here we have a sample of oxygen gas, has a volume of 420 milliliters at a temperature of 18 degrees Celsius. What temperature in Celsius will the volume be? 640 milliliters, assuming pressure and moles of gas are constant. Okay, so for this one, I'm going to list out the properties that they've given us. All right, just to save a little bit of room so we can manipulate the equation. So we'll say that our volume 1 is going to be 420 milliliters. Our temperature 1 is going to be 18 degrees Celsius. And we're going to want to take that 18 degrees Celsius and we're going to add 273 to it. 291 Kelvin. And we want to know the temperature at the new volume of 640 milliliters. So V2 is going to be 640 milliliters. And we are going to be looking for T2. Okay. So we're going to work through that process that we did before, where we start out with V1 over T1 equals V2 over T2. And we're going to isolate our T2 variable. So again, we start, first step, getting this out of our denominator. So I'm multiplying both sides by T2 over 1. And that's going to cancel my temperature from the right side and move it over to the left side. And what I'm going to be left with over here will be T2 times V1 over T1. And now to get the T2 by itself, I'm going to multiply both sides by the reciprocal of what's over here on my left side that I'm trying to move over to my right side. So that's going to be T1 over V1. And so you see my T1s cancel out, my V1s cancel out, and now whatever I used as a multiplier on my left side, I have to use that same thing on my right side. Okay? And now what you're left with, once you're done doing all that, is that T2 is all on its own. And it's going to be equal to V2 times T1 divided by V1. And now I can plug in my values that I've listed out here. V2 is going to be 640 milliliters. T1 is going to be 291 Kelvin divided by V1, which is 420 milliliters. Our milliliters units will cancel out. And we end up with 443 Kelvin as our final temperature. In this question, they wanted us to report our final temperature in terms of Celsius instead of Kelvin. So we're going to take our 443, we're going to subtract 273 from it. And we end up with a temperature of 170 degrees Celsius. And that is going to be our final T2 value. All right, let's look at this next learning check here where they're giving us a few fill in the blanks to work with. We're going to use the gas laws that we've talked about so far to complete the sentences with increase or decrease. So when volume decreases at constant pressure and moles, we're going to expect pressure to increase because it's inversely related. Okay. When temperature decreases, what does volume do? Volume is directly related to temperature, so volume is going to decrease as well. In part C, they want to know what pressure does, and the volume scenario they're giving us is a volume changing from 12 liters to 24 liters. So that volume is experiencing an increase, which means our pressure is going to be experiencing a decrease. And then part D is looking for us to see what our volume is going to do when our temperature changes. And that temperature change is going to be from 15 up to 45 degrees Celsius. So this is describing an increase in temperature, which means that we're going to be looking at an increase in volume as well. Okay. All right, next law. This is the third simple gas law. This one's called Gay-Lussac's law. And this one looks a lot like Charles' law. All right, the math is going to look really similar to Charles' law, but Gay-Lussac's law focuses on the relationship between pressure and temperature instead of volume and temperature. Okay, but you're going to see how it's going to look extremely similar in terms of the math, right? They're just saying with Gay-Lussac's law that the pressure that's exerted by a gas is going to be directly related to the Kelvin temperature of the gas. So if we're holding our volume constant and we're holding the amount of gas constant and we increase the temperature, we should expect to see a corresponding increase in pressure. Okay. So first question to look at here, solving Gay-Lussac's law for P2. All right, so if we're solving this for P2, this one's easy enough. Just again, it looks very similar to what we were doing with Charles' law. Here, our unknown is already in a numerator position, which makes our work a lot easier because we just have to multiply both sides by T2. And then what we're left with is going to be T2 times P1 divided by T1. And that's going to give us our new pressure, P2. All right. Let's take a look at this question here. A gas has a pressure of 2 atmosphere. I'm going to write down some of this information while we read it. At 18 degrees Celsius. So pressure 1 will be 2 atmosphere. Temperature 1 is going to be 18 degrees Celsius. What's the new pressure? So P2 is an unknown when the temperature is 62 degrees Celsius. So our new temperature has increased. Okay. So we start by listing out all of our properties. And I'd say before we even worry about what we're doing in the formula, make sure that we take these temperatures and we turn them into Kelvin. Okay. Now they're asking us to find a new pressure. Luckily, in our last question, we just walked through the steps of solving Gay-Lussac's law for an unknown pressure. So we can plug in our variables here, okay? T2 is going to be our 335 Kelvin times P1, which is going to be our 2 atmosphere, divided by T1, which is 291 Kelvin. And now that can just go in our calculator. And our new pressure is going to be 2.30 atmosphere. Okay. Let's look at the last calculation for Gay-Lussac. This one says that we have a gas that has a pressure of 645 torr at 128 degrees Celsius. What's the temperature in Celsius if the pressure increases to 824 torr, volume and moles of gas remain constant? So we're going to be increasing the pressure, holding the other things constant, and that means we should be seeing an increased temperature as well. All right, so erase the old stuff. Pause that so we can see the board. And our P1 is going to be 645 torr. Our T1, 128 degrees Celsius. Pressure increases to 824 torr. And we're looking for that T2 value. That's our question mark. So before we mess around with this, let's just take care of this temperature value, add 273 to it so that we have turned it into Kelvin. And now we're going to look at this equation and we're going to solve for our variable before we start plugging numbers in. Okay. So get the T2 value out of the denominator first, and then get it by itself alone on one side. Okay, so first thing we're going to do is multiply both sides by T2 so that we can get that unknown value out of our denominator position. And now what we're going to be left with is T2 times P1 over T1 equals P2. And now we want to get P1 and T1 over to the other side. So we're going to multiply our left side by the reciprocal of those values so that they cancel out on our left side. We multiply the right side by that same thing because whatever we do to one side, we do to the other side. And now we can rewrite what's left. T2 is going to be equal to P2 times T1 over P1. I know it's a lot of ones and twos. That's why you have to just make sure that you are keeping track as you go. So now we can plug in our values. P2 is going to be 824 torr. T1 is going to be 401 Kelvin. And we're dividing that by P1, which is 645 torr. Our pressure units cancel out. Our temperature is going to be 512 Kelvin. They want this temperature reported in Celsius. So once we get our Kelvin temperature, we'll subtract 273 from it. And we have a Celsius temperature of 239 degrees. Okay. All right, let's look at the next topic, related topic, but it's just like a little offshoot. Okay. Another part of gas pressure in general is looking at the vapor pressure and the boiling point of substances. We're most familiar with the boiling point of water, like that's our mainstay. But when we're talking about vapor pressure, we're talking about the evaporation of our liquid, specifically the particles that are near the surface of the liquid, right? Those liquid particles that are closest to air, closest to the atmosphere, those are the ones that are going to evaporate and turn into a gas first. Okay. So what we're saying here is that if you had an open container, like imagine an open glass of water, and you just left that water out on a table, eventually all of the liquid would evaporate. Okay. All of your liquid would at some point end up close to the surface of whatever liquid is left in the glass, and it would evaporate. When you have a closed container, though, and the gas doesn't have anywhere to escape to, it's not just like leaving the glass and then leaving the room and leaving the house. It gets stuck in the container that it's in. When that happens, the vapor, the gas particles that form, they're going to accumulate in that area that's above the liquid and within the container, and they're going to behave like gases. So those particles are just going to move around, they're going to collide into things, and when they collide into the walls of the container, they're going to create pressure. And we call that pressure specifically vapor pressure, because it's going to be the pressure of the gas that's formed by a liquid when it's like kind of sitting above its own liquid. All right. A liquid is going to exert its own vapor pressure at a given temperature. So whatever liquid you are looking at, that liquid will have its own vapor above it. And the act of boiling is going to be when the vapor pressure becomes equal to the external pressure. Okay, when the vapor pressure of the liquid matches the external pressure, that's when you see the boiling process happen. All right. Now, how is that related to what we know about like different altitudes and different boiling points? Again, if you think about places that have lower pressures overall, lower pressures mean lower atmospheric pressures, means that your water can boil at temperatures that are a little bit lower, because the vapor pressure of water is going to match the atmospheric pressure at a smaller point in terms of pressure, smaller pressure value. If you go to places that have a significantly higher pressure, well, not, I guess this isn't significantly higher, but 800 millimeters of mercury is definitely higher than standard sea level. So if you go here, if you go down to like the Dead Sea, where you're at a lower altitude than sea level, and your vapor pressure, your atmospheric pressure is higher at 800 degrees, at 800 millimeters of mercury, rather. If you try to boil water and you're keeping track of that temperature, you're going to see that water is boiling at a little bit above 100 degrees Celsius. Okay. So when you're at higher altitudes and your atmospheric pressure is lower, you're going to see a decrease in your boiling points. Lower pressure, lower temperature. But at higher pressures, you have higher boiling points. okay? And this is happening because specifically the higher altitudes, like in the mountains, your atmospheric pressure is going to be lower than the atmospheric pressure at sea level. And when we look at the vapor pressure, right? If something has to match the atmospheric pressure before it can boil, well, the vapor pressure of water is going to be able to reach the atmospheric pressure like at a lower temperature with less energy when when the atmospheric pressure is lower. That's why you're going to see that smaller boiling point when you are like high up in the mountains or something like that, when you're at an increased elevation. We have one more simple gas law to look at, but before we get there, I want to introduce this idea called the combined gas law, which is when we use sort of all the different gas laws we've looked at so far, and we can relate all of these properties to one another. Okay, we're going to use pressure, volume, and temperature of gases and say that we can change any two of these properties and figure out what's missing in our, in our new scenario. This is just an overview of the simple gas laws we've looked at so far, what their relationship is. This is the equation that we've sort of come up with. And this is our combined gas law, rather. Okay. Combined gas law means we're putting all three of these together. So instead of saying just P1 times V1 equals P2 times V2, we're going to include the temperatures in this as well. So what we end up with is P1 times V1 divided by T1. So we have all of our variables equals P2 times V2 over T2. Okay. And what they're trying to show us here in this part of the slide is the variable that's not included for this specific simple gas law. So in Boyle's law, we only focus on pressure and volume. We don't include temperature. For Charles' law, we only focus on volume and temperature. We don't include pressure. And for Gay-Lussac's law, we only focus on pressure and temperature. We don't include volume. All right. But we can sort of squish all of these simple gas laws together, and we end up with this combined gas law, which allows us to solve for more things. Okay. So here's just an example. We'll use the combined gas law to solve for this. We'll start by writing out the information that they give us. Let's label this combined gas law. Okay, and they're saying that a gas has a volume of 675 milliliters at 35 degrees Celsius and a pressure of 646 millimeters of mercury. Okay, it doesn't matter what you label. How do I want to say this? I'm calling everything that they talked about first 1. So V1, T1, and P1. Okay, and I'm listing them together because this volume is related to this temperature and this pressure specifically. Okay, so now in the next part of the sentence, when they say, what is the volume of the gas? So now in this second scenario, we're going to change something about our first set of conditions. So they're saying, what would the volume of the gas be? So it's unknown at negative 95 degrees Celsius. So now I've changed my temperature from 35 degrees Celsius down to negative 95 degrees Celsius. And my pressure changes from 646 millimeters of mercury to 802 millimeters of mercury. But we're still holding my amount of gas constant. Okay, so assuming the amount of gas stays the same, these are the things that we're changing. Okay. So let's start by changing our temperatures into Kelvin by adding 273. You always want to be in the habit of doing that, like ASAP. Okay, and then we can write out our combined gas law. P1 V1 over T1 equals P2 V2 over T2. All right. And our unknown in this case is going to be this V2 variable. So what's a really good idea, a really good habit to get into is going to be to isolate your unknown variable before you plug your numbers in. Because it's going to be a lot easier to mess up something in your calculator if you're trying to like move the numbers once they're already in your formula like this. If we solve for our variable first, then we're going to be putting everything in once it's already in the correct position. So if I want to isolate V2, what I'm going to do is multiply both sides by the reciprocal of the variables I'm trying to move over. So I'm going to multiply my right side by T2 over P2. And I'm going to multiply my left side by T2 over P2. Right? And then these two things are going to cancel out from my right side, and I'm going to be left with T2 times P1 times V1 divided by P2 times T1. And that's all going to be equal to V2. And now you have everything like where it's supposed to be. And so now you can just plug in from your list, just go in order, like T2, 178 Kelvin. P1, 646 millimeters of mercury. V1, 675 milliliters. Divided by P2, 802 millimeters of mercury. Divided by T1, 308 Kelvin. Okay, you're going to notice that your units are all going to cancel out, and you're going to be left only with a volume unit. And we end up with a new volume of 314 milliliters. Okay. Let's try one more. A sample of helium gas is a volume of 0.180 liters, a pressure of 0.8 atmosphere, a temperature of 29 degrees Celsius. At what temperature in Celsius will the helium have a volume of 90 milliliters and a pressure of 3.20 atmosphere? Okay, so they're giving us a new set of conditions to work with. And in this case, we're going to have an unknown temperature instead of an unknown volume. Right, so our original volume is going to be 0.180 liters. Our original pressure is going to be 0.800 atm. Our original temperature is going to be 29 degrees Celsius. And then our new volume is going to be 90 milliliters. Oh, that'd be nice and tricky here. Our new temperature is our unknown. And our new pressure is going to be 3.20 atmosphere. All right, so we have to fix our units before we can start plugging numbers in. And there's two things we have to fix here. Okay, first of all, we know we have to fix our temperature. So let's add our 273 there. The second thing that we have to fix is our volume units. For our combined gas law, there's not one specific volume that we must use all the time, but the volumes that we use have to match each other. Okay, so we either have to represent both volumes in milliliters or both volumes in liters. And it does not matter which one you choose to do, but they must match. Okay, so I'm just going to take this milliliter value, convert it into liters, because I had space over there. But you could have taken this 0.180 liters and used it as 180 milliliters to do the rest of the calculations that we're about to do. Okay, and now we're going to write out our combined gas law. And we're going to want to solve this for T2. And again, this goes back to what we said before. In this case, T2 is in the denominator, and it cannot be in the denominator. We have to first pull it out of the denominator. That has to be our first step. So we're going to multiply both sides by T2. And once it's out of the denominator, then we can isolate it. And we're going to isolate it by multiplying both sides by the reciprocal of the thing that we're trying to move. Okay, so if we multiply our left side by T1 over P1 V1, that means that this all cancels out from our left side. And now we have to multiply our right side by this same thing. Okay, and once we combine all of this, into one term that looks a lot less messy, what we're left with is T2 equals P2 times V2 times T1 divided by P1 times V1. Okay, and now that we have this set up, now we can go back into our variables that we've written down and plug everything in. So P2 is going to be 3.20 atmosphere. V2 is going to be 0.0900 liters. T1 is going to be 302 Kelvin divided by P1, 0.800 atm, divided by V1, which is 0.180 liters. Okay, and our atmosphere unit cancels out, our liters unit cancels out, and we're going to get a final temperature value that's in Kelvin. Okay, so we have a final temperature of 604 Kelvin, and this asked us to report it in terms of Celsius, so we'll subtract 273. And we get 331 degrees Celsius. Okay, just plugging this back in to make sure my numbers were good. Okay, so that would be your new temperature. And that is the combined gas law. The next thing we're going to talk about is the last of the real simple gas laws. This is called Avogadro's law. And this is going to work the same way as the other gas laws have worked, but the relationship here is going to be between the volume of a gas and the moles of gas, the amount. Okay. We'll get into this molar volume term in a second, but what we're looking at here is the relationship between the volume of a gas and the moles of a gas. We're going to see that just like with Gay-Lussac's law and Charles' law, the relationship between the volume of a gas and the amount of the gas present is going to be a direct relationship. So assuming that you're keeping your temperature and your pressure constant and they're not changing, when you increase the moles of your gas, if you want to keep everything else constant, you have to increase the volume of the container as well. If you decrease the moles of your gas, you'd have to decrease the volume of your container. And that's what you're seeing here. Like our overall pressure in this case can't change. So when we look at our first sample, we have this 1, 2, 3, 4, 5, 6 moles of gas, and we have 1 liter of space. So those 6 moles of gas are colliding with the walls of the container a certain amount of times. In our new scenario, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these little gas particles. So we have twice as much. And so in order for our pressure not to increase, we have to expand our volume by 2 as well, so that the amount of collisions that are happening is the same in both scenarios. So let's take a look at Avogadro's law, do an example here. Okay, and so for this one, we have V1 over N1 equals V2 over N2. And the question that we're looking at here is we have 0.75 moles of helium gas. Occupying a volume of 1.5 liters. And it says, what volume will 1.2 moles of helium occupy at the same temperature and pressure? So we have a different mole amount of gas, and we want to know what our new volume is going to be. Okay, so our V2 value is going to be our unknown. So in order to isolate this variable, we're going to multiply both sides by N2, which will move it over onto the other side, and it'll leave our volume variable alone. And now we can look at everything we've listed out here, and we can plug in what we know. Our N2 value is going to be 1.2 moles. our V1 is going to be 1.5 liters. And our N1 value is going to be 0.75 moles. And we're seeing an increase in the mole amount. So based on the direct nature of the relationship of these two properties, we would expect an increase in volume as well. All right, and we have a new volume of 2.4 liters, which is reasonable based on the increase in moles that we were seeing there. Okay, so Avogadro's law is just going to work the same exact way as our other stuff, as our other simple gas laws are working. All right. Okay, so now we've kind of gone through all of our simple gas laws. And we're going to start looking at different calculations, new calculations. Okay. Share my screen again. Okay, so when we're looking at gases, you're going to see a set of conditions that's going to be referred to as STP. Okay, and STP means standard temperature and pressure. The reason why we're going to use this STP scenario environment is because it's going to allow us to compare different gases under the same sets of conditions, same types of environments. So when we say that something is a standard temperature, we mean a temperature that is 0 degrees Celsius or 273 Kelvin. Okay, it's any temperature that's going to be equal to 0 degrees Celsius. For standard pressure, we're looking at any pressure value that's equal to exactly 1 atmosphere. So if you think back all the way to the beginning, when we looked at that list of all the pressures, all the numbers that were equal to 1 atmosphere, any of those numbers would be considered the standard pressure as well. So like 1 atmosphere, 760 millimeters of mercury, those would all be considered the standard pressure, okay? But the standard pressure has to be something that's equal to 1 atmosphere. The standard temperature has to be something that's equal to 0 degrees Celsius. And when you use the standard temperature and pressure, you can create relationships of the other properties, okay? So for example, molar volume is one of these other properties that kind of, it emerges once you apply your standard temperature and pressure. So what molar volume tells us is that if we have 1 mole of gas, only 1 mole of gas, just one, and we have that mole of gas at standard temperature and standard pressure, that 1 mole of gas, no matter what type of gas it is, 1 mole of gas is going to occupy 22.4 liters of space. Okay, so molar volume is this relationship. 1 mole of gas at standard temperature and pressure equals 22.4 liters. Okay. We can turn this equality into a conversion factor for ourselves, and we can use it with other calculations as long as we're at standard temperature and pressure, right? This is just an example of what we're talking about when we're saying 1 mole of any gas. If you look on your periodic table, remember your periodic table is in terms of grams of that gas per mole of that gas. So if we have 1 mole of helium gas, that's going to be equal to 4.003 grams of helium. 1 mole of helium is going to take up the same amount of space as 1 mole of oxygen gas, even though oxygen gas is 32 grams per mole. All right. So 1 mole of any gas, as long as we're at standard temperature and standard pressure is going to equal the same, it's going to take up the same exact volume, and that volume is going to be 22.4 liters. All right, so we have a couple of examples to look at. First one, what is the volume occupied by 2.75 moles of nitrogen gas? At standard temperature and pressure. Okay, so let's look at how we organize this. When you see that term, right? When you see this term at STP, it might be a good idea for you to like remind yourself of the equality that you're looking at here. 1 mole of gas equals 22.4 liters. This is a number you have to remember. Okay, we're not going to tell you that one for the exam. Like, you have to know what the molar volume is. Okay. Now, if that equality is true, which it is, then you can say to yourself, all right, well, I have 2.75 moles of gas. I know that every 1 mole of gas is going to take up 22.4 liters. So now I can multiply this out. And at standard temperature and pressure, my 2.75 moles of gas is going to occupy 61.6 liters of volume. Okay. Let's take a look at the next question here. Double question. What's the volume at STP of 4 grams of methane, CH4? And then how many grams of helium are present in 8 liters of gas at STP? Okay, let's write down those questions. So volume at STP of 4 grams of methane. And then grams of helium in 8 liters of gas at STP. Okay. We've got our 2 scenarios. Both of these are STP or at STP, so we know that we're going to likely end up using our molar volume equality at some point to help us answer the question. So we'll rewrite it up here. The molar volume relationship is between moles of gas specifically and the volume. What that means for us is that if we're given information about a gas, and that information is in terms of grams, we need to convert our gram value into moles before we can apply the molar volume. Okay. So step 1 here is going to be to take our grams, turn it into moles. And then step 2 is going to be to use the molar volume. All right. So to convert my 4 grams of CH4 into moles, I'm going to need to find the molar mass of my CH4. So I've got carbon and hydrogen. I've got 1 carbon. I've got 4 hydrogens. Now I'm going to look on my periodic table. Carbon's 12.01, hydrogen's 1.008. Now I'm going to add these together. We get 16.042. 16.042 grams per mole. That's my molar mass for my CH4. And so now I'm going to go back to the amount of CH4 that I'm looking at in my particular sample. I've got 4 grams of CH4, but I want to know how many moles of CH4 this is. So I'm going to use my molar mass, and I'm going to use my molar mass like it's any other equality. Remember that when you have something that's written out like this, like when we talked about with density before, I can rewrite this as an equality to make it a little more clear. I can say that every 16.042 grams of my CH4 equals 1 mole of my CH4. So now when I'm going to solve out this problem, I know that my gram value is going to go on the bottom in the denominator position, so my grams unit will cancel out. And my mole unit will go up top because that's what I want to end up with. Okay, so that's how many moles of CH4 I have. Now that I have my CH4 in moles, now I can use my molar volume. Because I have my mole value and I know that my molar volume says that every 1 mole is going to be 22.4 liters. So this is going to be my volume. Okay. That's for our first question. Our second question asks for something a little bit different, even though we're still using the molar volume. It's saying, well, how many grams of helium are in 8 liters of gas if I'm at STP? I can't use my molar volume to figure out grams directly, but I can use my molar volume to help me find the moles of helium gas. And once I know the moles of helium gas, then I can use my molar mass to find grams. Okay. So here I'm going to start with the number that they've given me, my 8 liters. And I'm going to set up my molar volume equivalency or conversion factor a little bit differently. Because here, my liters has to go on the bottom so that my liters unit will cancel out and my 1 mole goes up top. So if I have 8 liters of volume and I know that 22.4 liters is for 1 mole, I can already tell that I'm looking at fewer moles than 1. So my sample is only going to be 0.357 moles. Okay. And once I know my moles of helium, now I can use the molar mass of helium to figure out how many grams there are. When I look at my periodic table, I see that every 1 mole of helium is going to be 4.003 grams. they end up with 1.43 grams of helium. Okay. All right, let's look at the next part. This next section talks about what's called the ideal gas law. Share my screen again. And the ideal gas law is kind of like the culmination, the conclusion of all of those simple gas laws and the combined gas law that we've already talked about. Okay. With our ideal gas law, we're setting up an equation for ourselves that is able to relate those four properties of gas that we've talked about: pressure, volume, temperature, and moles. And it allows us to find a missing variable as long as we know the other three. So if I know pressure, volume, and temperature, I can find moles. If I know volume, temperature, and moles, I can find pressure. Okay? The ideal gas law allows us to do that. And the ideal gas law, I mean, it's going to look similar to what we've already seen. Here is its format. PV equals nRT. Okay? Hopefully at this point, some of these letters are variables that are familiar to you now. That P is going to stand for our pressure. Our volume, or V, is going to stand for our volume. Our lowercase n is going to represent our moles of gas. And our T is going to represent our temperature. Okay? The new part of this is going to be this R value here. And this R value is called the gas constant. And we're going to use the gas constant as kind of, it's like a proportionality constant. Okay. Your textbook talks a little bit about how it's formed. We don't have to worry too much about the how, but we do want to be able to use it. It is a number that you have to know. All right. This R constant, 0.0821, it has specific units that are associated with it. Okay. The value of this number depends on what these units are. Your textbook also shows you a different version of this R constant that you can use if the variables are different. But we're going to stick to this particular R constant. And the units that we're going to associate with it will be a volume that's in liters, a pressure that's in atmosphere, an amount of gas that's in moles, and a temperature that's in Kelvin. So that means that when you use your ideal gas law formula, PV equals nRT, you must make sure that the numbers that you plug into this formula are represented in these units only. Okay? So you can't plug a pressure in if it's in torr. You can't plug a volume in if it's in milliliters. You can't be putting grams of gas in. Can't have a temperature that's in Celsius. All right? You have to be really specific with your ideal gas law that you're plugging in numbers that have units that are represented in our R constant. The other thing with the R constant that you want to be mindful of is remembering this zero. This zero gets dropped out all the time in calculations, and it will throw off your final answer, okay? So remember, it's going to be 0.0821. And let's look at an example of how we apply the ideal gas law. A question that you might have is like, when do I know that I need to use the ideal gas law? And the answer to that is, like, if you have a scenario where you're not given a change in conditions, like in the other examples we've looked at, we said we have this first scenario And now we're like changing the temperature or changing the pressure, and we're figuring out a new scenario. With the ideal gas law, you're going to be given just one scenario, and you'll be told 3 out of the 4 properties of the gas that you're working with. And then your goal will be to find that 4th missing variable. Okay. So in this question, we're just going to write down the info first. Dinitrogen oxide, N2O, which is used in dentistry, is an anesthetic, also called laughing gas. What is the pressure? So we already know that our pressure is the unknown. In atmospheres of 0.350 moles. So our N value, 0.350. At 22 degrees Celsius in a 5-liter container. Okay. This is our information. We know that our ideal gas law is going to be PV equals nRT. We look at our units. The only unit that we're going to have to modify is our temperature before we can get started. Okay. And now when we're looking at our ideal gas law, we're going to be solving it for pressure, which means that we can isolate our pressure unit before we even begin plugging stuff in. Divide both sides by volume. And our equation is going to look like this. Pressure equals nRT divided by volume. So now we can plug in the variables. Our N value is going to be 0.350 moles. Our R value is going to be 0.0821 liters atmospheres over moles Kelvin. Our temperature, 295 Kelvin, divided by our volume of 5 liters. Now watch what happens with these units, okay? My moles here cancels out with my moles. My liters up here cancels out with my liters here. My Kelvin temperature here cancels out with my Kelvin here. And the only unit I'm going to be left with is atmosphere, which is my pressure unit, okay? And my pressure is going to be 1.70 ATM. It's like 1.695. So 1.70 atmosphere. Okay, so that's how you're going to use your ideal gas law. Pretty straightforward. Let's look and see how we work with gases that are in our chemical reactions next. We were looking at some of the stoichiometry in the last chapter, and we can apply that to chemical reactions that have gases in them as well. If we know how many moles of one of our substances we have, then we can use it to figure out how many moles of the other component in our reaction that we have as well. Just like we were doing with the other reactions, okay? It's just that when we are dealing with the moles of gas, we're going to be able to like use the ideal gas law in addition to that to give us the missing information, whatever we're looking for. I think this will be less confusing if we look at it in terms of an example. So in a question like this one here, it says nitrogen gas reacts with hydrogen gas to form ammonia gas. Okay. They give us a balanced equation, and they say how many liters of NH3 can be produced at 0.93 atmosphere and 24 degrees Celsius from 16-gram sample of nitrogen gas. 16 grams of nitrogen. All right, so first of all, they want us to figure out information about ammonia. They want us to like end up with a volume of ammonia gas, but they've told us a mass of nitrogen gas. Okay, so they want us to find a volume of this, but they gave us a mass of our nitrogen gas. So we're going to think about this in terms of steps. When you have a mass value that's given to you, and you have to use it in a balanced reaction or in the ideal gas law, the first thing you want to recognize is that the mass values are not going to be very useful to us unchanged. Okay, we can't use masses in a balanced reaction. We can't use a mass value in our ideal gas law. So when we're given a mass value, we want to take that mass value and we want to use it to find the moles of whatever it is we're looking at. Okay. So we have 16 grams of nitrogen gas, and they're saying that our pressure is 0.93 atmosphere, and our temperature is 24 degrees Celsius. Okay. So let's pause for a minute. All right, so step one, we're going to take this mass value and we're going to find out how many moles of nitrogen do I have. All right, so I'm going to take the mass of the nitrogen. I'm going to look on my periodic table, find the molar mass of nitrogen. I'm going to put my gram value on the bottom so that my gram units cancel out. Okay, so that's my mole value for my N2. Second step, we're going to find the moles of NH3 from the moles of N2. And we're going to do this by using our balanced equation. All right, so our reaction, N2 plus 3H2 gives us 2 NH3. And we know that when we're looking at a balanced reaction like this, that we're looking at mole equality, excuse me, mole equalities here. So we can write this out and then we can say like 1 mole of N2 equals 3 moles of H2. 1 mole of N2 equals 2 moles of NH3. Or 3 moles of H2 equals 2 moles of NH3. Those are the equalities we can write out from our balanced equation. So here, if I want to know how many moles of NH3 are going to be equal to my 0.571 moles of N2, I'm going to use my equality that links those things. Okay, I got 0.571 moles of N2. And I know based on my balanced equation that every 1 mole of N2 is going to give me 2 moles of NH3. Okay, it's my second step. The third step is you have to remember that this question's saying like how many liters of NH3 are going to be produced. So right now I have my moles of NH3 and I have the other pressure and temperature variables here. But step 3 is going to be to use the ideal gas law to solve for volume. Okay, so my ideal gas law, PV equals nRT. And if I want, I can rearrange this to say that volume equals nRT divided by pressure. Okay, before I plug in my numbers, I want to make sure that I convert my temperature into Kelvin. And now I can plug in the values that I have. My N value, my mole value, that's going to be my moles of NH3. My R value is going to be that same gas constant. My temperature is going to be 297 divided by my pressure, which is 0.93 atmosphere. Okay, and again, I like going through the steps of crossing out the units, sort of verifies that I've done everything correctly in terms of my setup. And I see that the volume of my gas is going to be 29.9 liters. Okay. So that's how you can use the stoichiometry that we've already worked with. Our balanced chemical reactions, we can link one part of the reaction to another part as long as we know the moles of one thing. All right. Okay. The next thing that we want to talk about with the gases is called partial pressure. Partial pressure is this idea that when you have a mix of gases together, that they are all going to contribute to the overall pressure of the container that they're in. Okay. But each individual gas that's in that mixture of gases is going to have like its own pressure value associated with it. So you can see partial pressure like in action in a lot of places. You're seeing some examples here because you're looking at mixtures of gases that are in blood. So there's a big like oxygen carbon dioxide balance that's constantly in flux in your body, depending on the part of your body that you're in. And you're going to see that both of those gases are going to contribute to the overall pressure But at some points, the pressure of the oxygen is going to be greater than the carbon dioxide. And in other parts, the carbon dioxide is going to be greater than the oxygen. All right, so it's just going to be like the back and forth of it is sort of how the oxygen moves through your body. But we're going to look at a few different types of gas mixtures and sort of see how they work. This idea of partial pressure, again, it's linked to the individual the individual contribution of like a single gas that's part of a gas mixture. Okay, so what you're seeing here, we have helium in this tank, we have argon in this tank. And in this third tank, we've put both of those gases into the same tank, all right? So in our first tank, we have only the helium, and the pressure of the helium is 2 atmosphere. In the second tank, we have argon only. The pressure of argon is 4 atmosphere. Now, when we mix them both together in this new tank, they're both sort of retaining their own pressure, their own identity, and they're applying it to the new tank that they're in, their new environment. So to figure out what our new total pressure is going to be, we're going to add together the pressure of each individual gas. Okay, so your total pressure is equal to the sum of the individual pressures that make up your gas mixture. All right. That idea is called Dalton's law of partial pressures, because I guess Dalton was the first one to think it up. We're going to see that the pressure depends on just the total amount of gas particles that are present and that are present in your mixture and that are doing all of the colliding. The pressure doesn't depend on the type of gas particle. Okay, so the pressure isn't affected by the fact that you have different gases. The only thing that's going to matter in terms of pressure is how much of those gases are present and how often they're colliding with the walls of the container. Okay, so to figure out the total pressure that's exerted by a mixture of gases, you're going to add together all of the partial pressures that are present. Okay, PT stands for pressure total. So this is going to be your total pressure. And then each of the individual pressures will be given like its own little notation. So what we've got here, we have an individual gas all on its own. We have 1 mole of nitrogen. The pressure is 1 atmosphere. In this second example, instead of just having 1 mole of a gas, we have 2 different gas samples, 0.4 moles of oxygen, 0.6 moles of helium. It adds together to 1 mole, and the pressure is still going to be 1 atmosphere. This is going to be true at standard temperature and pressure, obviously. The correlation between 1 mole of gas occupying 22.4 liters is only going to be true at standard temperature and pressure. But for all of these, we're seeing that the identity of the gas doesn't matter. So we have just nitrogen here. In the second container, we have oxygen and helium. And in the third container, we have oxygen, helium, and argon. The amount of gas in all 3 of these containers is the same. 1 mole, 1 mole, 1 mole. And that means that each of these gases, whether they're an individual gas or they're a mixture of gases, is still going to exert the same amount of pressure. Okay. The air that we breathe is another example of a gas mixture. Oxygen is our, it's kind of like what we're hunting for when we breathe, for our lungs and for oxygenating our blood. But when we're breathing in gases, that gas is a mixture of a lot of other things. Okay. most of the gas in the air that we breathe is going to be nitrogen. And the next most important component is going to be oxygen. After that, it's a mixture of some other things: CO2, argon, water vapor, potentially anything else that's floating around in the air. And sort of this total air contribution, the total that makes up our atmosphere, is the combination of all these things. When we add all these things together, when we add the pressure, the partial pressure of each of the individual contributors, those partial pressures add up to 760 millimeters of mercury, which is our atmospheric pressure. We can also look at the amount of each gas in terms of a percentage, just to get an idea of the breakdown. You see that like nitrogen is our biggest contributor by far, followed by our oxygen. When we're looking at problems that have gas mixtures in them, so for example, we have here a scuba tank contains oxygen with a pressure of 0.450 atm and helium with a pressure of 855 millimeters of mercury, obnoxiously in different units of pressure. What's the total pressure in the tank? Okay, and we're assuming that the volume and the temperature are constant here. So for us to figure that out, we just need to understand that in order to find the total pressure, we have to add these individual pressures together. Okay, now obviously in this case, we have pressures with different units attached to them. So we're going to want to convert one of these before we start doing any of our math here. And in this question, they're asking for the total pressure to be in the units of millimeters of mercury. So when we start doing this, we'll focus on converting our oxygen pressure into the millimeters of mercury unit. Right, but let's write this stuff down. We have oxygen, so we're going to write that the pressure of O2 is 0.450 atm. The pressure of our helium is going to be 855 millimeters of mercury. And for us to find the total pressure, we're going to take the pressure of oxygen plus pressure of helium. Okay, but before we can do that addition, we have to convert our oxygen pressure into the correct units. So let's write a little aside here so we can put our unit equality. Every 1 atmosphere is equal to 760 millimeters of mercury. Okay. So when we set up our conversion, we're trying to get rid of our atmosphere unit. So atmosphere goes in our denominator. 760 millimeters of mercury goes up top. All right, so that is oxygen's pressure, but written with units of millimeters of mercury instead. So now when we go to find the total pressure, it's going to be the pressure of oxygen plus the pressure of helium. And that's going to be the total pressure that's in our tank. Okay. Let's look at the next question. So here they're telling us that For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atm. So that they're saying that that mixture has a total pressure of 8 atmosphere. Okay, and then they're saying that the pressure, if oxygen has a partial pressure of 1280 millimeters of mercury, what is the partial pressure of helium? All right, so let's organize this information. They're telling us that the total pressure of our mixture is 8 atmosphere. And then they're telling us that the pressure of our oxygen is 1280 millimeters of mercury. And we're trying to figure out what the pressure of our helium is going to be. Right? So one problem that we run into here is that we have the different units again. If you notice that the answer choices are all listed in terms of millimeters of mercury. So when we're deciding between these two units, which of these values we're going to convert the one whose units are different than your answer choices. Okay, but you have to make sure that the units are the same before you can do any math. So we're going to take our 8 atmospheres and we're going to set up our conversion. It's the same conversion we used in the last problem, but this time our 1 atmosphere has to go on the bottom so that our atmosphere units cancel out. All right, I think that's how we had it set up last time as well. And then we're going to have our 760 millimeters of mercury up top. So this is going to be our total pressure value. Okay. And for Dalton's law of partial pressures, we said that P total is going to be equal to the pressure of gas 1 plus the pressure of gas 2. Okay. So our P total is 6,080 millimeters of mercury. The pressure of our oxygen is 1280. And we're still looking for the pressure of our helium. So we'll subtract the pressure of the oxygen from both sides. And we end up with 4,800 millimeters of mercury as the pressure of our helium gas. Okay. So that's how our partial pressures are going to work. Let's just take a little look through some of the rest of these slides, which really talk about how the different body systems are affected by partial pressures and movement. This is just a blown up picture of what we looked at earlier, but here you're seeing in your lungs, your oxygen is going to enter the blood and your CO2 is going to be, your CO2 that's in your blood is going to be released from it. That's sort of the process that's going on in your lungs, but in your tissues, your oxygen is going to enter the cells. And then your cells are going to release CO2 into the blood. Right? So this is where this is how this all gets connected. Why is there CO2 in your blood? Well, the tissues are putting it there because they don't need the CO2. What they need is the oxygen. So it's very cyclical that way. And you're going to see the pressures change based on where you are in the body. When you're in the tissues, the pressure of your oxygen, less than 30, pressure of your carbon dioxide is greater than 50. And so your tissues are going to get rid of some of that carbon dioxide. All right, it's going to enter your blood, and then it's going to travel around, and then eventually it's going to get booted. It's going to get exhaled, right? It's going to get booted out of your system in those exhales that you take. And when you inhale, you're going to be increasing the amount of oxygen that's present in the system. If you want to break down about if you want to look at the partial pressure and what's happening in terms of that, like why is oxygen flowing into the tissues? Because the partial pressure of oxygen is higher in the blood and it's lower in the tissues. And so you have that, you'll, I mean, think about it like diffusion. Okay, it's not exactly the same thing, but you can get an idea of of how it's working if you think about it like diffusion. Like if you spray something in the corner of one room and then you go and wait on the other side of the room, eventually you're going to smell that thing, right? Because like the particles, the gases are going to travel. They travel to wherever, from where they're most concentrated, they're going to travel out to where they're least concentrated. And while it's not the exact same thing, it's a similar idea here where like, why is oxygen flowing into the tissues? Because there's a lot of oxygen in the blood and there's less oxygen in the tissues. And the oxygen is going to move into the place where there's less of it. All right. Why does CO2 flow out of the tissues? Because there's a lot of CO2 in the tissues. And so the CO2 is going to move out of the tissues into the blood because it's going to move where there's less of it. All right. You know, when you get later on in like your studying and stuff and in future classes, you can look at some of this in a little more detail, but that's like the general idea of what's going on there. And these are just some numbers to back that up. Take a look at that. You can look at an overall breakdown of how the partial pressures of the gases that are in the different parts of your body change during the breathing process, which is kind of interesting. You can watch like your nitrogen levels change or oxygen levels change, depending on where the air is, like in the breathing process. Okay. But all of that breathing is just, it's like partial pressure of gases in action. Okay. But hopefully that topic makes a little more sense now. And that's pretty much it for this chapter. Okay, so just practice with some of these problems. Make sure you go back and you try some of those examples on your own without watching the work right away. The best practice that you can get is trying some of these questions out without seeing them worked out and just see how far you get. And then if you get stumped, you can watch through the explanation. And then you're like, all right, well, here's where I made my mistake. Here's where I got lost. And then you can kind of fix that. Okay. Other than that, let me know if you have any questions.